Okay, why don't we go through this? Y'all want to go through this?
Yeah.
Yes, please.
Okay, so first thing you have to do is you got to get the region right. Okay, I'm going to go kind of fast, all right? So the region is bounded by sine x, right? And cosine x, and x equals 0, which is the y-axis, right? So the region we're looking for is just that right there. I'm not kidding. Okay?
Figure that out.
Okay, so you need to know this endpoint, which that's when sine and cosine are the same. That's when sine equals cosine, and that's going to be at pi over 4. Right? That's where your x and your y coordinate are the same on the unit circle. So that means 45 degrees or pi over 4. Right? Okay, and we start at 0. So that's the first thing, right? You got to get that region right. Now, going around, let's go part A. We want to do part A, we want to go around the x-axis, right? So that region, let me redraw it. Here's the x-axis. We got something like this, and then something like that, roughly. Okay. We want to go around the x-axis. Then, and these are both written as y equals and y equals. These are both functions of x, right? Which means if we want to go around the x-axis, which method are we going to want to use? Washers or disks. So that is when our rectangle, right? When our rectangle is perpendicular to our axis of rotation, we want to use washers. So for part A, I'm going to use washers. And the formula for washers is basically pi integral from the starting x value to ending x value. So 0 to pi over 4 is where we're going to slide that rectangle through. And then it's going to be the outer radius, which is the distance from the axis of rotation to the outer edge of the rectangle, and then minus the inner radius squared, both of them squared. So this should be what? Cosine squared x minus sine squared x dx. That's it. That's the first one. Okay? Now, if I want to take this and do part B, and I want to rotate now around the y-axis, which is here, right? My axis of rotation is here. My rectangle's like this. I'm going to want to use shells because my rectangle is parallel to my axis of rotation. So for part B, using shells, my formula is 2 pi integral 0 to pi over 4 again, and then the all-important radius, which is always the distance from the axis of rotation to your rectangle. So it's from here to the rectangle, and that distance is actually the same as the distance from here to here, which is always x. In this particular problem, our distance from axis of rotation to our rectangle is x. So it'll be x, that's our radius. Then, what's the next part? Top function minus the bottom. So top function is cosine x minus sine x dx. How did I get what?
Did you get x then?
X is always the distance from the origin to the rectangle. Because x is going to vary between 0 and pi over 4, right? So this rectangle is going to start off over here at 0 and then slide its way through to pi over 4, right? The distance the rectangle has moved will always be the variable x. That's part A and B. Part C. Ready for C? E? What? E? I'm going to do C. So C, difference here, C, we have this region we're going to go around y equals -3. So here's our region. Okay, and we want to rotate around this line now. Okay, and this is down at -3. So again, I'm going to use washers because my rectangle is vertical. So my axis of rotation is horizontal. So I'm going to use washers for part C. Washers. Which means my formula is pi integral 0 to pi over 4. And now I just need to know the outer radius squared minus the inner radius squared. The outer radius is the distance from the axis of rotation to the outer edge of the rectangle. Distance from here all the way to there. And then the inner radius is distance from here to here, right? So that distance, the distance from the x-axis to the top is the cosine function, right? And then the distance from here to here is just 3. So my outer radius should be 3 plus cosine x. So I do 3 plus cosine x, but it's that squared. Then minus my inner radius, which again is the distance from here to here, but that's this distance, which is sine x plus 3. Doesn't matter what order you do those in. Like, you could switch those. Squared dx. There you go. That's part C. Part D, the difference between C and D is that instead of y being negative 3, we have y up here at 5. So our axis of rotation's up here now, right? So I'll do another picture. Yeah, you just have to be careful getting these correct. So here we go. So this is y is 5, right? So here's my rectangle. Washers again. Okay, so D, washers. And my outer radius is distance from the axis of rotation down to the outer edge, which is here, right? That's my outer one. Let's see, what is that distance?
5
So this is 5, right? But you want to take away this much, and that's sine x. So you're going to be doing pi integral 0 to pi over 4. And then the outer radius, which is 5 minus sine x squared minus, now you do the inner radius, which is the distance from here to here, which is 5, take away this height, which is cosine x squared dx. Yeah? Part E. So part E, you want to go around x is negative 4. So for E, got this picture. Negative 4 is over here. That's my axis of rotation. Same region. Rectangles this way. Shells, right? Parallel. Okay, so I need to know, let's see, 2 pi integral 0 to pi over 4. And then the all-important radius. Okay, the radius is the most important thing for shells. So we already said that the distance from the origin to the rectangle is always what? X. And then the distance from here to here is 4, right? So we want to know distance from the axis of rotation to my rectangle. It's going to be 4 plus x. And then it's just top minus bottom again. So cosine x minus sine x dx. And then for f, I want to go around x equals 10. So here's 10. Like this, again, parallel shells. Okay, so I'm going to go 2 pi integral 0 to pi over 4. Okay, I need the all-important radius. This is the one that gets people tripped up. From here to here is x, right? From here to here is 10, but we're trying to find from here to here. That's our radius, right? So what's that? 10 take away x. So this is going to be 10 take away x, that's my radius, and then top minus bottom again. Cosine minus sine dx, done. Okay, those are the integrals.
It's so easy when you do it.
It is.
So if we like completely bombed it, like completely.
Well, the United States did a lot of bombing this weekend, so you should,
I mean,
right? I mean,
sure.
don't feel bad about bombing.
I mean, yeah.
I don't know what to tell you. I got to look at the whole class. Yeah, I mean, I want that at least you got the first, like, hopefully you got like 2 out of these 6 right, you know?
I know how to do like all the other stuff, but like not trig. Because it wasn't hardly any trig in the homework. That was just brewing.
But there was that take-home quiz, right? And on that take-home quiz, you had to find out where sine and cosine were equal to each other. That's why I gave you that, because I'm like, okay, they did one like this already, right? Didn't you have to figure out where sine and cosine were equal? Oh yeah, in that quiz, I'll pass it back. There was another quiz that y'all did, I think, in groups that I still need to put the grade in for. But I have the grade for that sign one. And I took off on some people if they, and you can come argue with me if you want, and we can discuss it, but I did take off if you did not show how you found the intersection of the two curves. Like a lot of you that did those cosine that went up the y-axis on this quiz, I'll just pass them around. Actually had the had the correct intersection points, but you never showed how you did it. So you had to have written down something like sine y equals cosine y, and then some people did, some people did. I didn't take off a lot, but I just, Okay, y'all ready? We're gonna get to new material today. Unless y'all want to discuss this topic anymore. So someone went to the tutor and got some help, right? Or y'all were asking tutor about something? Be aware that I think most of the Cal 2 classes here that are taught here, they do not do the section on shells. Okay?
Your schedule doesn't have it either.
Yeah, it's probably not in. I just always build it in. I just always cover it. So the reason I'm saying this is that a lot of times tutors won't even be aware of the shells method. But the shells method is, it's super nice because, just think about this. If we had this same problem we just did, right? And I wanted to rotate that region around here, right? We kept the vertical rectangles, right? So it made it nice because shells allows you to do that. If you didn't have shells, you could only do a horizontal rectangle. You could only do washer method, which means you need a rectangle that goes like that. The problem is these functions are not functions of y, they're functions of x. So the first thing you would have to do is convert these functions over from functions of x to functions of y, which means you'd have arc sine and arc cosine involved. And you would also have to split it into two separate integrals because on that top part, it's this curve, right, on the right side. Left side would be this line. And then when you get down here below, it's going to be a different curve. So it just becomes super complicated. With shells, we can kind of do it all, right? So it's nice. So am I moving on or am I not? Yes.
So with the shells, we basically never have to turn it horizontally with the rectangles?
I'm not going to say never, okay? Because what if the curves that were given to you originally were functions of y instead of functions of x? Let me just show you an example. What if you had something like this? X is equal to y squared, and x is equal to y squared plus 1. All right, let's just look at that. If we were to graph that, not 1 minus y squared. Let's just do that. So if we did that, we'd have a parabola opening up sideways like this, and we'd have another parabola that opened up like this, roughly. And let's just say in quadrant 1, just to make our lives easier. So only looking in quadrant 1. So we're talking about this region right here. Okay? Got it? If I want to rotate that around all 6 different combinations, like if I wanted to go this way, right? Then because these are solved for x, these are functions of y. So it would be, again, difficult for me to use vertical rectangles here. Does everyone see that? Vertical rectangles would not be as fun. But I could do horizontal rectangles all day, couldn't I? Because my right function and left function are just these two, right? So if I want to go around, let's say, the x-axis, I would use shells because my axis of rotation is parallel, right? So what I would do instead is I would find out where these hit each other. If I was doing shells, I'd do 2 pi. Integral would go from, I'd be working with y coordinates because my rectangle is going up and down. So I believe they hit at 1. So 0 to 1, 0 to 1. And then I would do the radius, which is a distance from my axis of rotation to my rectangle, which now is not x. What is it? It's this distance, which would be y. So that would be y. And then instead of doing top minus bottom, I'm going to do right minus left. And so I would do this one, which would be 1 minus y squared, minus the left one, which is just y squared. I hope that makes sense. It's basically everything but switched. And then if I wanted to wrap it this way, right, I would keep my rectangle like that, and to wrap it around this way, I would go to washers. Does that kind of make sense or no? So in theory, if you can see both of those, then yes, you can always just use shells and washers to do everything. Yes?
So why is it always y before the arc line at all?
Well, it's not always y. It's y in this problem because I'm rotating around the x-axis, and the distance from the rectangle to the origin is always y. If our rectangle was turned the other way, the distance from the origin to the rectangle would be x. It just depends on what you're oh, I forgot dy here. It depends on what you're integrating with respect to. I'm pretty much on your test going to keep everything nice functions of x. I might give you one of these in the beginning to calculate the area of. Because we did a section, when we first started this stuff, we did areas between curves, and there were both when you have functions of x and then functions of y. All right, anything else before I move on?
So just to make sure, like the rectangle that you put in the graph is going to be with respect to the axis in which it's wrapping around, or sorry, the functions you're given. So in that one you were given x equals, so you know it's going to be a horizontal. Mm-hmm. And if it's a y equals, it's a vertical.
Yes.
And then the axis in which you're given to rotate determines whether to use washer disc or
Shells.
shells.
Yes.
Okay.
That's a perfect summary of it. If it's solved y equals a function of x, you're going to have vertical rectangles. Okay? And therefore, if you're going to wrap this way, you're going to use washers. But if you're wrapping this way, you're going to be using shells. If you're given your curves and they're solved for x, right, then your rectangle is going to go like this. And if you wrap this way, you'll use shells. And if you wrap this way, you go washers. Good.
I have it now.
Okay, good.
Can I take the quiz again?
You take the quiz again, right? Okay, we've eaten up a good 40 minutes of class. Let's proceed on now. So we're going to cover 2 sections today because they're quick sections. 7.4. These I don't believe I have in the notes. Arc length. Okay, arc length. So for arc length, we're going to kind of change up a little bit of our visual approach to the problem. So far what we've been doing is taking these regions, wrapping them around different axes or different lines, and finding volumes, right, of these things that were formed when we did it. Now we're kind of just going to take a step back. We're going to go and take a look at a curve. Okay. Let's say that this is some curve, y equals f of x. And let's say we're going to draw that curve just between A and B. I mean, we can find the area under that, right? That's one thing we can do. I give you a function, give you an interval. I can say find the area under it. I can say wrap around the x-axis, y-axis, all these different lines. But this is different. I want us to imagine taking this graph and just picking it up off the page and straightening it out. Okay? Like it's a string. Taking it and then pulling it taut. And then measuring how long it is. That make sense? How can we come up with that length? That would be called the arc. That would be called the arc length. So it would be like measuring, if I had to walk through this, how far I would travel, right? So the idea here is that what we're going to do is we're going to zoom in. I'm going to zoom in on like this little infinitesimal piece of the curve, all right? So I'm zoomed in on this thing. And what I see there is this curve that looks like that, right? It's this little piece. And what I'm going to do is I'm going to kind of cut that and just make 2 little points there. So there's 2 little tiny points really close to one another in here. And that's what I'm looking at, right? Zoomed in like a billion times. And then I'm going to construct a right triangle here across like this. And as we move across this curve, you know how we've had these rectangles we've been putting in here, right, to get the areas? And we said how wide was our rectangle if it was vertical? How wide was it? It was dx, right? That was dx. That was like this little infinitesimal width, wasn't it? It's how much our x changes as we move, just little tiny infinitesimal change. So if I'm looking at here, if I'm going to go from this point to this point, then this little infinitesimal change in my x direction would be dx, right? And then the change in the y direction would be dy. And of course, if we connect these together, like that with a straight line, then would you agree that that straight line is that hypotenuse is approximately equal to the length of that curve? And if I zoomed in even more, I would get a better approximation, wouldn't I? If I zoomed in even more, it'd be better and better. Eventually, this hypotenuse becomes that length if I can zoom in far enough. And by zooming in, what we mean is making the dx get smaller, right? And that's exactly what happens when we do this, right? When we did the integrals, we did the rectangles, we said we wanted an infinite number of rectangles, which means they all have to basically have a width that goes to 0. If this width goes to 0, the blue line, the length of the blue line becomes the length of the black curve in the limit. Do you all buy that? I mean, we've been buying it for a while, so I hope we can buy it now. Yes? So what I'd like to do is see if I can come up with a formula for the hypotenuse length, right? And then that would represent the length of one little infinitesimal piece, and then I want to add them all up. And how do I add them all up? Bring an integral in, okay? So we just need a formula for this. The formula for the hypotenuse, just using the Pythagorean identity, would be dx squared plus dy squared square root, right? That would be the length of that. A squared plus b squared is c squared, so c would be equal to the square root of a squared plus b squared. Now that would be the formula, and we would want to integrate that, wouldn't we? We would want to do an integral that would add all those up, and we would want to move across. We would want to move across from a to b, wouldn't we? So we would want to go integral from a to b of this. And that's it. That would be the formula, right? Somebody gives me a curve, y equals f of x, and I want to figure out how long that curve is. Then what I'm going to do is I'm going to do this integral of the square root of dx squared plus dy squared. We on board? Problem with that integral is I'm not really quite sure what this is. Like, what is dx and what is dy? And I don't even have like a with respect to any variable out here, right? Before, that dx naturally was here, right? Because it was the width of the rectangle. Or the dy was here because it was the rectangle turned the other way. There's nothing out here now. Do you see that? So to get to it, here's what I'm going to do. I'm going to remind you that when we have this equation right there, if I ask you to take the derivative of this equation with respect to x, okay, take derivative of this with respect to x, and I want us to use Leibniz notation. Okay, Leibniz was like d something, d something. So the derivative of y with respect to x on the left side would look like this, dy dx, equals, and then the derivative of the right side, I'm just going to write f prime x. Do you all agree with that notation? I mean, you learned that in Cal 1. The derivative of a function with respect to x is actually dy dx. Yes? Okay, now what I'm going to do is I'm going to take that and I'm going to solve it for dy. If I take this and solve for dy, I get dy equals f prime of x dx. Do you all agree with that? Yeah? Now I'm going to come into this equation and I'm going to replace dy with f prime of x dx. So I'm going to say integral a to b square root of dx squared plus f prime of x dx squared. So when I square this right here, I square each one, don't I? I square the f prime and I square the dx. If I do that, then I'm going to have a dx squared here and a dx squared here, which means I can do what with it? Factor it out, and then I can actually take it out of the root because it's squared. So my next line is going to look like this. I'll stick it right here. Integral a to b square root, okay, so I may have done too much of that algebra. Let me just put it under here. This next line is f prime of x, that thing, squared times dx, that thing squared. So that's me squaring each one, that and that. And then I take the dx squared out of both of these and then take it out of the root. So when I take it out of the root, it's just dx, right? It's not dx squared anymore, it's just dx. And I'm going to slap that back here to the back of the integral, like that. And then what's still inside? I pulled dx squared out, so I have 1 plus what? F prime of x, that quantity squared. And that's an integral we can work with. Because that means in order to find the arc length, all I need to know is where I'm starting and ending my x values. I need to know the derivative of the function, which I can take, and I need to square it and then add 1 and take the square root, right? And I'm going to do this integral with respect to x. And I'm in business. Yes? Questions?
Is that like, I don't know if so is that like the formula that we're going to be using for the
Yep,
next time? Or
this is it.
Is there any reason that we're going to be swapping it, like doing dx over dy and then?
Yes. Let's do one application of this, and then we'll look at what you're bringing up. All right? Good?
Just out of curiosity,
Yes.
are we going to have to solve to get to that, or is that?
No, this is our master formula now.
That's what we're gonna be
Yeah.
using for, okay, good. That's, you're just showing
Yep.
how we got to it.
Yep. I just want to show you where it comes from. When I can show you where things come from, I will. When it's within, reason, I think this is within reason. So it's a nice geometric proof too, right? So, all right. So now let's do it. Let's do an example, and let's start off with a very simple one. Let's start with something like so simple that we wouldn't even need the formula, all right? Let's take y equals x, that function right there. And let's look at this on the interval 0 to 1. And I want us to find the length. Oh, by the way, that length, that integral that I had up here, I'll put it on the side here. We usually say capital L equals integral a to b of square root of 1 plus f prime of x squared dx. Okay, so capital L is the length of the arc length, or the arc length. So let's find the length. So let's just draw it real quick. Y equals x, only on the interval 0, 1. I want to know how long that is. Do we know how long it is? Without doing any calculus? Square root of 2. Should be square root of 2, right? Because this is 1 and that's 1. And this is really like a triangle. So this would be 1 squared plus 1 squared is 2. Square root of that's root 2. So our answer should be root 2, right? Let's confirm. All right, so for the formula, what do we need to know? We need to know the derivative, right? What's the derivative of this? Is 1, right? What is the derivative of that thing? Squared. Well, still 1, right? I'm just figuring out what these pieces are that I need for the formula. What's 1 plus that? What's 1 plus the derivative squared? That's just 2. And then what's the square root of 1 plus the derivative of that function squared? Just root 2, right? You see how I'm just putting it all together? I'm just kind of building it up. All right, so I just need to integrate root 2, don't I? With respect to x from 0 to 1. So the length of this should be integral 0 to 1 of root 2 dx. That's pretty easy antiderivative, yes? Because that's just a constant. So the antiderivative of that is just root 2 x, right? Evaluated 0 to 1. Plug in 1, what do you get? Root 2, plug in 0, what do you get? 0. Root 2 is the answer, and that matches up with what we already knew starting the problem. That's pretty straightforward, yes? Okay. Well, let's do something a little more complicated. How about we try how about sine x? So what this is saying, we want to find the length, okay? Find arc length. What this is saying is that if we were to graph our sine function just from 0 to pi, take that off the page, straighten it out, how long is that, right? How long is that first arc of the sine function? Right? That's what this is saying? So let's build up. I like to always try and just build up the integral. So we're going to start off with the derivative. So the derivative of this function is cosine x. Okay, we need to take that derivative and square it, which would be cosine squared x, right? And then we need to do 1 plus that, which would be 1 plus cosine squared x.
Halfway, half.
1 minus cosine squared x would be sine squared x, right? I need the square root of this. So 1 plus the derivative of this thing squared, which would be the square root of 1 plus cosine squared x, right? That's the thing I'm working with. And I'd have to integrate that from where to where. So to find the length, I need to do the integral from 0 to pi of the square root of 1 plus cosine squared x dx. Understand the setup? All right, now in terms of actually doing that integral, any ideas on how to integrate that?
Convert it to that quantity to the 1/2.
The one, oh, like a power reducing?
Yeah.
Like a power reduce? We could maybe power reduce that. The square root throws everything off, doesn't it? That square root just makes everything problematic. You know? Okay, just to kind of save us a little bit of time, I'm gonna go to my computer, and I'm gonna go to Wolfram Alpha, maybe, if my computer wants to respond today. Wake up. I'm going to ask Wolfram Alpha to integrate so the square root of 1 plus cosine x squared. Classes will be a breeze. Unlock, just pay, just pay. Oh, okay, so here's the answer. The integral is the square root of 2e of x, 1/2 plus a constant. Well, we knew this was coming, right? Plus a constant. Okay, what is e? Okay, e. E of xm is the elliptic integral for the second kind, or of the second kind, with the parameter of m equals k squared.
Makes perfect sense.
What? Okay, so that means basically we have gone to places that we don't know exist yet, okay? Which means that integral is not going to be doable for us at this point, all right? It's just not possible. Now, I'm going to change the instructions, and I'm going to say do that integral as a definite integral. So I'm going to say from 0 to pi, and that's going to be the actual length, right? That first question I asked was for it to just give us what the antiderivative was. But now it's saying, oh, it's the square 2 root 2, this elliptic blah, 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 which is approximately 3.8202.
Perfect.
So that's the numerical answer. And the way they got from this to this answer with the approximation is by using power series, which is chapter 8, which is, I'm trying to show you the value because, now I'm sure I'll say this again. Right now, and I think I have said this already, if we were to put all the integrals that could ever exist into a bucket, you know, and just close our eyes and reach into the bucket and pull out an integral, the chance that we can actually integrate it by hand is like practically 0. All right? So we have to have other ways of doing it. And power series allow us to do that. And we can get approximate answers. And these answers, even though they're approximations, you can go out as far as you want. So you could, like, this answer might only be accurate to the first 4 decimal places. But if we ask Wolfram Alpha to go out further, like, I'm sure this is smart enough to do it. Can you say just, oh, more digits? It's even better. So they'll give you more precision here. Oh, is that enough? Is that enough? Okay. I was curious though, could I just up here, could I just say correct to 15 digits? Let's just go with that. Let's just see what it does. There it is. Okay. So it can do that as far back, right, as far as we want. And that's why even though approximate answers sound like bad answers, in the real world, right, if you're going to sit there and let's say you're building a very precise bearing for some aircraft engine, there is a certain tolerance that your machine can't even get that accurate, right? So your math only needs to be within a certain precision anyway, right? So approximate answers are basically good enough, better, well, as good as the exact answer. Make sense? Okay, so aren't we interested in knowing how we would do that integral then? No? Okay. You're interested in knowing how Wolfram Alpha would do it, like how to go there, right? I mean, this is a highly debated thing. Like, why learn, right? Why learn this stuff if you can go to a website and have it do it for you, right? What's that? Yeah, but it's made now, right?
These kind of problems are why they invented calculators if you study the history of computers.
Uh-huh.
It's because of these kind of problems.
These things, yeah. We needed numerical answers.
Machine.
Yeah, because the method's there. We understood at some point, like power series and how great they were, but you needed a machine to do it because it's just a repetitive, high operation count thing. But it's just multiplication, addition, and subtraction. That's all it is. When I was in school, I took a class called numerical analysis. Okay, and it was a senior level math course. And the project that we had for the semester was, there was this thing called the black box idea, basically, that engineers and, well, this is a problem. Let's say you have a structural engineer who needs to build a bridge, right? And they bring up some computer program, and they're trying to figure out, like, what materials they need to use, how thick does the beam need to be, all this stuff, right? So they type in all these things into the computer, right? Input. And then the computer kicks them their output, right? Tells them, okay, this is how thick the beam needs to be, blah, blah, blah. But the actual engineer has no idea what went on between here and here, right? They trust that answer. They trust people's lives on, that answer, right? So my project in this class was I had to take 3 commonly used software platforms. And I had to basically go in and find any algorithm that was built into the machine already. So, maybe it was, I don't know, just to be simple, like the square root function or something. Something that was pre-programmed into the machine. I had to look at the code for that algorithm. I had to find weaknesses in that code. And then from the weaknesses, I had to come up with a problem where I could prove theoretically what the correct answer is, but know that when it goes through the black box, it's going to give me an incorrect answer. So I had to basically force the machine to give me the wrong answer. Does that make sense? Yeah. And so that is why, now, do we all need to continue to know all of the theory behind it? Not necessarily, but the people who are coding it have to, right? They have to understand that, with machines, there's all sorts of rounding issues that you run into, and you can only go out so many digits, and anyway, okay, so that's why I think it's important that we keep within math courses, the fundamental ideas have to stay here. I think they do. And this is a math course, right? This is not an engineering class, is it? This is a math class. There's a difference between engineering and math, right? Now, do you need a lot of math to do engineering? Yes. But it's still a math course, so somebody in here is still may be wanting to study pure math. So this is, we got to keep it, right? Okay, I'm done arguing. All right, so the moral of this, the moral of this story here with this problem is this. As innocent as sine x looks, and as nice as it would be to find that arc length, that didn't work out well, did it? And so it turns out, because of the complexity of the formula itself, square root of 1 plus the derivative squared, we have to be very careful in terms of just handing you a problem. Like I can't just like make problems up here. If I do, there's a potential that you can't do it, that I can't do it, all right? Because we can't do the integral. So the problems that I will do in class and that you have on your test have been carefully tailored to work, all right? So let's do another one of these that works. So I want to do this one. This is a problem that I really like because the algebra involved in this one is a little bit messy, but it's doable. Okay, let's go with this. How about y equals x cubed over 3. You know what? I've done that one. I thought there was another one I liked in here. Yeah, we'll do this one, because the algebra in this is so nice. Plus 1 over 4x. And we're going to do this on the interval 1, 2. So I want to find the length. Okay, I didn't put that up there, but I want to find the arc length of this curve. Maybe we'll graph it when we're done. So we're going to need the derivative, right? We're going to need to square the derivative. We're going to need to add 1 to it and take the square root and hope we can integrate that, right? So let's start doing my derivative. I'm going to use a different notation. I'm going to need to use y prime instead of f prime of x. So the derivative of this, what is the derivative of that? Remember, this is, if this helps, this is the same as 1/3 x cubed plus 1/4 x to the negative 1, right? That's the same expression up there. It might be easier for us to take derivative of that. So what do we get? First term is what? X squared, and then minus 1/4 x to the negative 2, right? Negative 1 comes out, and then you subtract 1. That's it right there. It's our derivative. And then don't we need to square that? We need to square that. And then don't we need to add 1 to that? Okay, so let's do the square of that first. If I square that, I have to multiply it times itself, which means I've got to do like an expansion or foiling, if you like. Right? All right, so when I expand that, let's see what we get. X squared times x squared is x to the 4th. And then what about this one right here, that multiplication right there? What's x squared times negative 1/4 x to the negative 2? Just minus 1/4. That's it, because the x's cancel each other out, right? You're adding the exponents. So you just get minus 1/4. What about the next one, the inside one? Minus 1/4 again. And then what about that last one? Be a little careful on that last one. Plus 1/16 x to the negative 4. Right? Just add the exponents. Negative 2 and negative 2 is negative 4. All right, that is our derivative squared. I'll continue that up here. That's x to the 4th minus 1/2 plus a 1/16 x to the negative 4. That's where I am. What are we supposed to do with that? Add 1 to that, right? So next line, what is 1 plus that derivative squared? Okay, so if I add 1 to that, it's going to just hit that thing, right, and just become 1/2. So I have like x to the 4th plus 1/2 plus a 16th x to the negative 4. This order doesn't matter, right? I'm adding the formula, remember, this formula, says I have to add 1 to that derivative squared, right? That's what the formula says. So I added 1 to this, and so it became positive 1/2 instead of negative. Right? 1 take away 1/2. Okay, we good? I need to take square root of that now and then integrate it. And it doesn't look pretty, does it? I mean, just initially here, the square root of this, but let me go ahead and just write the whole integral down now. I'm going to be doing the integral. What are my limits of integration? 1 to 2. And I'm doing the square root of that. X to the 4th plus 1/2 plus 1/16 x to negative 4 dx. You are not allowed to do that term by term, right? You cannot just go in here term by term, and you definitely cannot break this into 3 square roots. Okay? So we are kind of stuck right now, but it's not as bad as it initially looks. Remember, I said this problem had to be like very, very carefully made for you, right? Just for you. Just for you. You know, I read something today, I don't remember where, that made me just take that deep breath. And it's like a sigh. This is happening more as I get older. It was a whole column written about making sure that you choose your costume for Halloween to not offend people. And I'm just sitting here thinking to myself, how sad things are. Like, man, the costumes that I grew up, with were just so much fun. You didn't have to worry about offending people, or, that some costume you wear today is going to come and show up 30 years from now and prevent you from getting a job. I just feel sorry for these kids, can't have any fun.
Not even safe to go trick or treat, no. Some weirdos out there.
Oh, now there's weirdos out there?
Now
They're always there. They're always there. Yeah. Okay, so I've done this, right? And I'm going to get a common denominator now between all 3 terms. What's my common denominator? I'm sorry. I'm just saying. I'm just glad nobody's was sensitive. No, never. I'm stopping. I'm stopping right now. I'm stopping right now. I know. I'm on camera. I'm on camera. Okay. What's my common denominator? 16x to the 4th, right? So this first one, I'm missing a 16x to the 4th, so I have to multiply top and bottom by 16x to the 4th. So that's going to give me a 16x to the 8th on top there. Right? And then what is this one missing? 8x to the 4th, top and bottom. And then what about the last one? It's not missing anything, right? So just plus 1. And then all over my common denominator of 16x to the 4th. Now, I mean, you're sitting there going, what in the world? Why would you do that? Yes? I mean, maybe. But do y'all see the top? What happens on the top? This up here is almost like a perfect square trinomial. Like you can factor this up here. What is that factor to be? Let's see. I'll give you a hint. It's something squared. What is it? It's 4x to the 4th plus 1 times itself. Do y'all buy that? This right here, if you were to take 4x to the 4th plus 1 and multiply it times itself, you would get back this. It's kind of like this. If I put this on the board, I would hope that everyone understands that factors to be x plus 1 squared. Right? It's that principle cranked up a little bit to this. And then the bottom, right? The bottom 16x to the 4th, that's the same as 4x squared. Well, I don't even need that. I can just leave it. Just leave it as 16x to the 4th. Now, what's good about rewriting it like that? I can do the root on the top and bottom separately, can't I? So the root of the top is just going to kill the squared, and the root of the bottom is going to be 4x squared. So things are going to go, the root's going to basically vanish in the next step, which is great. So I'm going to have on top 4x to the 4th plus 1 over, I have to say it. I'm going to mute the microphone. I have to say it. I mean, no, seriously, like, now. This is integral 1 to 2. Now we just split into 2. Just split this into 2. This is x squared plus 1/4 x to the negative 2 dx. Now without the square root, we've got it, right? I did this over this. I did this over this. And now I can do those term by term. Let's go ahead and just get the antiderivative of this because we're so close already. Antiderivative is 1/3 x cubed. All right, what is the antiderivative of that? Yeah, negative 1/4 x to the negative 1 is the antiderivative of 1/4 x to the negative 2. We're evaluating this 1 and 2. So 2 goes in for x, 1 goes for x. We subtract, we got an answer. Good? So that problem, again, I mean, how special did it have to be for this to actually algebraically become something we could handle? It had to be very special, all right? You okay with that? All right, let's continue. I'm going to run out of time, but there's one thing I want to do here.
Still thinking about it. The Bears.
I should have just like wore like bear mace or something.
Do you actually have that?
I have some bear mace.
No, you don't.
Yeah, because we went to the Rockies this past, forget when it was, but yeah, we had bear mace because we were on trails. We didn't, thank goodness. But I am scared of them. Okay, so look, this is a problem that we've looked at before. Okay, so you have just an arbitrary circle. And what are the things that I've shown you in here about arbitrary circle radius r? We've proved a couple of things. It is arbitrary. But there's something, what did we do? We proved that the area of a circle is pi r squared, right? And we proved that the volume of a sphere or ball of radius r is 4/3 pi r cubed, right? We proved that. So we're talking about arc length right now. What do you think I'd like to prove here? That the circumference of a circle is 2 pi r, right? Wouldn't that be nice to just see where that formula comes from? Okay, so let's prove that this circumference is 2 pi r. So the way I think we should go about this is let's just look at that curve right there, that piece, and let's just find the arc length of that piece and then multiply the answer times 4. Yes? Now to do this, I need to rewrite this as a function of x, so I need to solve for y, and we have done that twice already, right? We took the arbitrary equation of a circle, x squared plus y squared equals capital R squared. We solved it for y, and that's what we got, right? Okay, so that is my f of x. If I'm going to do the arc length formula, what's my integral going to go from? So this right here is going to go from 0 to capital R, and then it's the square root of 1 plus the derivative of that thing squared. So I've got to take the derivative of that. All right, here we go. Derivative of that, well, derivative of the square root of anything is 1 over 2 times the square root of that anything, whatever was there. Chain rule says now times derivative of what's inside. What's the derivative of what's inside? So remember, capital R is a constant. So capital R squared is a constant. So the derivative of that is 0, right? Derivative of that, 0. Derivative of that, negative 2x, right? Okay, so that's our derivative. These 2's cancel. I can slide that x on top, right? What's our derivative squared? Square the top, x squared. Square the bottom. What do you get when you square the bottom? Just capital R squared minus x squared. Yes? All right, I need to add 1 to that. Y'all are looking like something's wrong. Are y'all okay?
Where did the 2 go?
With the other 2 canceled.
Oh,
Stop doing derivatives for like 5 seconds.
Okay, so now 1 plus that derivative squared should be 1 plus x squared over capital R squared minus x squared. What do you think I'm about to do here? I'm going to put them together because I'm going to do a square root, right? So I'm going to get a common denominator. So when I get a common denominator, that's 1 over 1, right? So I've got to put R squared minus x squared on the top and bottom, and then put them together. And when you do that, you should get R squared on top over R squared minus x squared. Do you all believe that that's the way to work? Common denominator. And then I need what? Square root of that, right? And I think it's time for the integral. Let's go ahead and go right to the integral at this point. The length of that blue piece should be the integral from 0 to capital R of the square root of that dx. Now, because I have a square root of fraction, I can do the top and bottom separately, right? Top and bottom separately. That means the square root of the top is just what? R, and R is a constant, right? Which can come out of the integral completely. So my next line is going to be capital R integral 0 to capital R. And then on the top I have 1, because I pulled the capital R out. And on the bottom, I still have to do the square root of this, right? Which I can't do algebraically, right? I can't do that. Like I can't do the square root of each one, so I'm stuck with that. And then you look at that and you go, trig sub. And there's actually, we could do trig sub right here, but there's a formula for this specific case. This is arc sine. Is it 16? Yeah, it's formula 16. Okay, but if you were like, well, using formula 16 is cheating, then you could always get formula 16 by doing trig sub, right? So the formula for this means should be capital R, and then the antiderivative of that should be arc sine of whatever the variable is, x, over whatever this constant is. So in the formula sheet, it's a. For us, it's r squared, right? So this is going to be over capital R. That's your antiderivative. And we're evaluating this from 0 to capital R, like that. So the first thing we'll do is we'll plug in capital R. So when we plug in capital R, right, we're going to have two things here. We're going to subtract. When we plug in capital R, we have R times arc sine of capital R over capital R, and then we're going to have R arc sine of 0 over capital R.